Hi, welcome to the lectures of CHEM2005 Chalk and Talk summaries. Today we will talk about the synthesis of indoles. In the last lecture we were talking about the properties and reactivity of indoles, and today we will see how we can synthesize indoles. The retrosynthesis is not easy. Basically you have to memorize that if we want to synthesize an indole, what we need to do is first separate this. We will use two molecules. Okay? We will use this part that I will put in green. I don't know if we will. Okay, the part in green will be a hydrazine. While the red part will be a ketone. A ketone or an aldehyde that has to be a position that is enolizable. Okay? This is very important and we will see why. Okay, this is the retrosynthesis. Okay, as I told you, it's very difficult to see it. Basically, I don't think that it's possible to see that this can be synthesized for a hydrazine. Okay, but you have to learn it, you have to memorize this retrosynthesis, and it's easy. Only follow this rule. The green thing is the hydrazine. Instead of a NH, we have a NH2, and the red thing is where we have the nitrogen. This is an enamine. If you take a look, this looks an enamine. This is coming from a ketone. Okay, good. Then, what is the mechanism? We start with we always add acid media. Okay, we start with the hydrazine and we add the ketone. What will happen is that in acid media we will protonate the ketone, making this carbon more electrophilic. Okay, well, this is a ketone or an aldehyde. I am saying ketone, but could be any carbonyl group. Okay, and then the pair of electrons of the nitrogen attack here to form the hydrazone. Okay? And as usual, this is an equilibrium. What we get is this compound here. Okay? Then this hydrazone tautomerize. This is, if you only check this part of the molecule, this is an imine. Okay? That means that can tautomerize to enamine. What will happen is that what we have, this is an equilibrium also. And we have the enamine here. And now what is happening is that we have an irreversible free sigma-cropy rearrangement. Okay? This you will see it next year. But basically, what is happening is that the enamine goes here, this goes here, and this goes here. Okay, we have this jump of electrons. The two electrons of the double bond of the enamine is going to the aromatic ring. The pair of electrons of the aromatic ring are forming an imine with this nitrogen, and we break the nitrogen-nitrogen bond to form an imine here. obtaining this compound. Okay? Then what is following, we have a rearomatization. Okay, we do the rearomatization. Okay, adding the hydrogens, moving the hydrogens a little bit, and what we have is this compound here. When we have this compound, the pair of electrons of the min are attacking the enamine. Okay, we can protonate first the enamine. Okay, and what we got is okay. Then we need to eliminate this nitrogen. Basically what to do is to protonate to make a better leaving group. And okay, and basically what is happening is that leaving group is departing, and what we have I will draw it here. We have the carbocation that now we can do the elimination of this hydrogen. And what we get is the final indole. Okay? This is the mechanisms to get an indole. The most important thing is that we form the enamine. Until the enamine, all the steps are equilibria, and the irreversible step is the sigma-cropic. That means what decision we take in the enamine after the sigma-cropic rearrangement will be fixed. What means this? Well, I put a very nice example that we only can do the enamine in one side. But what will happen if we are using, for example, the following reaction? Okay? Now I will do it a little bit faster, the mechanisms, but you have the step-by-step mechanisms here, and you have the step-by-step mechanisms in the lecture notes. Okay, what happens if we are using this compound? Okay, if we are using this compound, okay, remember we formed the imine. Okay, we form this imine, this is the key intermediate, and then we form the enamine. And in this case, we can form the enamine in this side, I will put in red, or in this side, I will put in green. We care. Well, in this example, we don't care. Why? Because we have exactly the same substituent in each side of the ketone. That means that we will get the same enamine. But what happens if instead of this enamine, instead of this ketone, we are using this ketone? Clearly now, we have two different enamines, that each one, I will draw here the first one and the second one, each one will lead to one product. Okay, this is the first enamine. And this will be the second enamine. Okay, if we do the sigma-tropic rearrangement, okay, we do exactly the same as before. What we'll get is, in this case, we get this intermediate, that will lead to this aromatic compound, that after the closing and elimination, I do it all in one step, I will get this final compound. Please try to do all the mechanisms. Okay, this will be the final product of one, and if we do exactly the same with this, what we will get is we get, with the sigma-tropic rearrangement, that will lead to this aromatic product, that after the closing we will get this product. That means when we are using a non-symmetric ketone, that means that the two sides of the ketone are not the same, or if we are using two different sides, what we will get at the end is two different products. Which product will be the major product? Well, this is depending on the stability of the enamine. Okay? And the stability of the enamine is the same that any double bond. That means more substituted, more stable. Okay, we can know which is the major product. However, we always will have a mixture of products. Okay, that means a priori doesn't seem a good method to do it. Okay, when we have asymmetric ketones, when you do these disconnections and you get an asymmetric ketone, I will say that this is not a very good method to do it. Then, how we can do it if we have an asymmetric ketone? When we do this disconnection, we have an asymmetric ketone. Okay, well, when we have an asymmetric ketone, what we need to do basically is, instead to do this deconnection, what we will do is this disconnection. Okay? What we are doing is putting an aldehyde. Why? Because clear, here we only will have one enemy. Okay? And if you do all the process, what we will get is this. Please do it at home, step by step. What we will get is this compound. Okay, and then the only that we need to add is R1. Okay, how we do it? Remember, we can do the lithiation of this position because this hydrogen is the most acidic. How? First we protect the nitrogen. Remember, we did this the day before. Okay, and then basically we add LDA or terbutyl lithium, whatever you want. Okay, and we add R1. Could be in the form of an halogen or acyl chloride. What is needed? Depending on the substituent, we will do one thing or another. And then remember to do that protection with TFA to get the final product. Okay? This is how we do it. When we have asymmetric ketone, what we will do is to use the aldehyde. We synthesize this compound, we sort R1, and then we add the R1. I can put an example. For example, we want to do this compound. Okay? I want to do this indole. We do the disconnection that we did before. One is the hydrogen, and then I do this ketone. 1, 2, 3, 4. 1, 4. If I am not wrong, is this ketone. If I use this ketone, when I will arrive before the sigma-cropyl rearrangement, when I am doing the enamine, I have two possibilities. The enamine in this position, in the internal position, that will be more stable, and the enamine in the smaller position, in the less substituted position. That will be the less stable. However, I will have a mixture of products. That means that this will not be a good method. What I do is basically I change. I put the aldehyde. If I put the aldehyde and I do all the mechanisms, please do it at home. Okay. What I will get this, then I want to do the anion here, that means I need to protect the nitrogen. I use Bock anhydride. Okay, and then would add, for example, methyl iodide. Okay, what is happening is that, like I explained the other day, I make the ion here, SN2, and what I get is this compound. Okay, with a box here, sorry. Don't forget to deprotect, and then TFA to deprotect the box, and I get the final compound. Okay? This is the most difficult synthesis that you will face. A synthesis that we don't have asymmetric ketone. Okay, and this is all about the synthesis of indoles. Okay? I hope that you understood how it works in the synthesis of indoles. Please, all these reactions that I only put the final result. Please do it at home, all the mechanisms. This will be good in order that you memorize or learn the mechanisms. Okay? And see you soon in the next lecture.